This video is going to cover how to do shear and moment diagrams the graphical way. Honestly, I find the graphical way to be a lot simpler than anything else, but it does have its tricks to it. And they're really not that bad. I have here in this lovely example that you can see, I've tried to create pretty much every weird scenario that you could possibly have. The blue values are my loads that were external, and my pink values are my reaction forces. So step one, of course, any problem is to do the statics and actually solve for your reaction forces. And I know you can do statics because you wouldn't be in solids if you couldn't do statics. So I kind of skipped that step for you. Now I will tell you that those numbers of 2.1 going down and 16.1 going up, they technically had a 2.5 at the end of them. And when you start rounding, you're going to realize that your diagrams might be a little bit weird at the end. But again, when that happens, I'm going to tell you why. And so just remember that it came down to where I rounded here. So if you go to 3 sig figs pretty early on, you might run into some problems. But anyway, what we're going to be doing is creating the shear and moment diagrams, obviously for this wonderful beam. And as you can see in the green, I've kind of listed out all of the distances between each point. And step number one, if you're doing these by hand, step number one is to come through and add in a vertical line every time there is effectively something new. So whether it be a reaction, which is a force, right, a concentrated force, we're going to come in, we're going to add a vertical line. So that's what I did here. Point moment, put a vertical line, point load, vertical line, another point load, vertical line, a distributed load where it starts, vertical line, where it ends, vertical line, and yet another point load, vertical line. Pretty much anytime there is a new thing involved with your lovely loading situation, put a vertical line. The reason we have these vertical lines drawn is to help you remember something is going on either in the shear or the moment diagram, especially when we have these goofy cases here, because it's really easy to forget about him if you don't put the vertical line, and he's going to cause you some problems at the very end. So what we're going to start off doing, of course, now that we did figure out our reaction forces, is we're going to start obviously by solving for shear. So shear is first. You obviously can't do the moment diagram unless you have shear, because if you recall for shear moment diagrams, the load diagram determines the shear diagram, and the shear diagram effectively determines the moment diagram. There's lots of little bits and pieces to go along with that, with calculus and all that, but just to sum it down into some baby things. For the shear diagram, in order to create it, if the load goes up, your shear diagram's going up. If your load's going down, your shear diagram's going down. If you have distributed loads, it's going to go down, obviously, across every itty-bitty little step. And every time that you go from a horizontal line for your load up here, this is a 0 degree, every time we go to the next diagram, so we go from load, we go into shear, this one's going to have a 1 degree. When we go from shear into moment, this is going to have then a 2 degree. We're always increasing the degree of curvature for our slopes. So again, this is going to make a lot more sense as we get to it. First things first though, we're always going to start and stop at 0. If you don't end at 0, and we're always going to work left to right. If you don't end at 0, you messed up. That's the only nice way to put it. So before we get started though, the most important thing for you to do is label everything. Everything, everything, everything. If you think that it could possibly have a label, it needs a label. So things that might be very obvious, should be very obvious, that aren't unless you label it, positive and negative. Yep, that's right, positive and negative. Definitely need to label those. Units. If these are kip feet and kips for our things, and kips per linear foot, then our shear is in kips and our moments are in kip feet. Units are so important. This way, all of the numbers you're going to put on this chart have units. So how shear is going to work? We're starting at 0 and we're working left to right. So we're starting here and we're going to move over. If you see a load, we're going to add it. So here we go. We've got a load going down right there. It's down 2.1. Going down is negative. So we're starting at 0, and step number 1, we're subtracting 2.1. What does that get us to? Obviously negative 2.1. So again, we're starting at 0. Don't forget to label that. And we're going to go down straight to 2.1. Ta-da, there we go. Straight line, did it. Now, as we go over, nothing's happening. This moment, nothing's happening. All the way until this 7 kip force right there at that line. So while nothing's happening, do you know what that does for our shear diagram? Nothing. Yes, in fact, absolutely nothing. It means that there is no change at all until we hit that line. No change. That's a 0 degree slope. Don't forget to label it. So no change at all. Right? That doesn't mean that it's 0 shear. It just means that there's no additional shear. Literally, if you just take a cut, right? We go back to equilibrium of a deformable body. If you take a cut here versus taking a cut here, and you find the shear force, you're going to discover it didn't change. Hence, what we're actually doing on this diagram is just denoting that anywhere in those first 5 feet is not going to change. Then once we get to that 7 kips, what we're going to do is we're starting at negative 2.1, and then there's another 7 kips. 7 kips goes down, that's negative. So minus 7, what are we at? Minus 9.1. Okay, go a little bit further. Minus 9.1, maybe we're right here. We're going straight down. Arrows say go down, we go down. Then what? Nothing's happening, nothing's happening, nothing's happening. We hit this line. So let's draw it out. We've got nothing happening until this line. What's happening at this line? Well, we're starting at negative 9.1, and we want to add, because arrow go up, 16.1. What is that going to give us? Positive 7. So, okay, all the way up here, we're going to go to positive 7. Say maybe like there. The whole reason that we're going to label every single thing that we do is because, let's be honest, none of this is to scale. So because of that, you definitely want to explain to somebody what these values are. Always don't forget your degree of curvature. So that was a 0 degree down there. Now what? Nothing's happening, nothing's happening, nothing's happening until we hit this distributed load. So here we go. I'm not going to erase that. That one's scary. Here we go. So here we go. We're going to nothing's happening until right here. So again, that's a 0 degree. Now for the fun. We can't just analyze the entire distributed load all at once, because we have to analyze it at every step along the way. So if you were to imagine taking a cut and find the internal loadings at every single one of those points, that's what we're doing. So as we go along to all of these itty bitty little points, so far everything's going to be the same. It's going to keep increasingly going down, 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 down until we hit that 5 kip, and then it's going to start doing weird stuff. So when we're doing distributed loads, you have to go until there's another change in loading. Be careful about those. So we're starting at 7 currently. Arrow goes down, which means minus. What is the magnitude of the force right now that's going down in this area only? In that area only, that's going to be, this is a rectangle, so base times height. The base is 2 feet. The height is 3 kips per foot. So again, feet are canceling, and we're left with kips. So good. So what is 7 minus 2 times 3? Just 1. So we're going to go straight down, oh, not straight down. We're going to go down at an angle here, down to 1. So of course I'm going to 1, and that's going to be about right here, connect this with a straight line to the best of our ability there. Ta-da! So we're going down. That was a 0 degree up there, so this is a 1 degree, right? Linear line, just think degrees are literally the degrees of the polynomial. If you were to write the equation of this line, that's y equals mx plus b. That's just x to the first degree. That's where this came from. If you write the equation of this line, that's y just equals some number. There is no x. That's x to the 0 degree. So that's where it comes from. And now that we're at 1, now we have to analyze this guy. So there's 5 kips going up. So we got 5 plus 5 here. We're going to end up at 6. So we're about right there. So straight up towards 6 at this point. And now that we're at 6, now we're going to come back through and analyze now the rest of this distributed load. So what does that get us? Again, we're starting at 6, and we're going to subtract, because arrows go down, the area of under that curve, which is base of 2 feet, height of 3 kips per foot. Again, the feet cancel, we're left with kips. And 6 minus 2 times 3 is 0. That means, yes, we did make it back to 0. Good job. If we didn't hit 0, we have a problem. So again, depending on how well you actually drew this diagram, actually to scale or not, those slopes that you had should have been the same. But my drawing is quite atrocious, and I'm doing my best here to actually line that up and failing miserably. So there we go. We're just going to kind of come in here. Okay. Not really liking me there, bud. There we go. Ta-da. Really didn't like me. So again, label it one more time, 1 degree. Now some people think, why do I have to label distances at this point if you've drawn a lot of lines? Well, because you should always label your distances. So yes, you're going to come back through also and label any distances. Key things of note would definitely be if you're going to cross with a kind of linear shape here. If you're going to cross 0, where you cross 0 is very, very important, because that's going to create an inflection in our moment diagram. And what that means is a change in direction of the shape, right? Because currently shear go down here is meaning that moment is going down, 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 down. Then this part here is positive, which means that it's going to change and go up, 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 up. So where it crosses 0 is a really, really, really big deal. So no matter what, label every single distance that you know. So this is 3 feet, this is 2 feet, this is 3 feet, that's 2 feet, that's 2 feet, that's 2 feet. Is it redundant? Doesn't matter, label it anyway. Why? Because now when we go to the moment diagram, mainly we want to look at the shear diagram. When we're looking at the shear diagram, that's effectively what we need. We need all of the values. Now, the only thing that should be picking your brain right now is the fact that this is all the same. So why the line? Why the line? When you're actually doing this, you're thinking, okay, that's effectively turn these into distributed loads, right? Your shear diagram now becomes load, and now we're going to do the same thing for moment that we did for shear. We're just going to treat the shear as if it was load and do it all over again. So when you're looking at that, you're going, why do I have a vertical line there? That's kind of weird, because there's no extra thing going on. And the reason we did that was to remind you that, hey, you have a moment. Yes, you have a moment, so do not forget about him. So great. So now that we're not going to forget about that guy, let's talk about how do we do the moment diagram. Starts off the exact same, also ends the exact same. Yes, we have to start and stop at 0 all over again. So this time maybe I'll do it in blue. So we're starting here at 0. Gonna label it. There we go. There's 0. So same thing. Shear go down, moment go down. Kind of the same. In order to get the directions of the slopes, 0 to 1 degree, that's pretty easy. If it's negative, obviously the slope of your line is going down. That's pretty simple. But when we get to these over here, these 1 degrees, and then they got to become a 2 degree, right? Because every single time we go from one diagram to the next diagram, we have to increase in our shape. So when you go from a 1 to a 2, that's when the question becomes convex or concave. There's two different ways to do everything, right? You could have a slope going like this, cool, like that, or it could have been like that. Both of those are going from a point 1 to a point 2, but whether it be concave or convex is really the question. So in order to do that, I created my own little 2-point rule. There's another video on that. So if you are kind of struggling with that topic of going from the 1 degree to the 2 degree, or perhaps even the 2 degree to the 3 degree, I would go give that video a look. But again, it's going to start pretty much the exact same, right? So we're going to take into account our moment here, our shear. We're starting at 0 for our moment. So we're at 0. And what does the shear tell us to do? Again, we're going to go between each line as we look at things. So what does the shear tell us to do? The shear says go down this value. So of course the area is going to tell us the magnitude of change that we're going to make. So what is that area? That area is going to be, and this is negative, so we're going to go down, so that's minus. What's the area of that curve? Well, it's the base of 3 feet times the height there of 2.1. So we're going to get that one is minus 6.3. So again, that's a 0 degree. So we're going to go to minus 6.3, maybe about there-ish. And that's going to be a straight line. Hopefully my ruler doesn't fight me this time. Nope, totally fighting me the whole way. Thanks. So there we go. We went down to 6.3. All right, now what are we doing at this line? Well, it is obviously very much so not anything to do with the shear diagram. That has to do everything with this glorious 10 kip foot applied moment. And moments are kind of tricky because this is an external moment. And because it's external, the direction it's going is not the direction that the internal's going. Remember, when you make a cut, gotta kind of resist it, right? So this is how I remember it. I could say it in like 3 or 4 different ways, but the one that I feel is best and easiest is I'm gonna take a look at effectively, erase that. I'm gonna take a look at right here. What's going on? If I just cut it at like right here and just consider this beam right there, what shape am I getting? I'm just going to use my brain here and say that I've got 10 kip feet going this way. If I have 10 kip feet going that way, statics reaction says, well, you got another 10 kip feet going this way, right? Cool. So if I've got a beam, just imagine like a ruler. Take a ruler right now. Or imagine a ruler and take your hands and put your fingers in the direction of that moment. And as you're coming around and you're going to push up, right? You're going to push up on the center of this beam. What shape is that going to make this beam? Well, that means that this beam is going to pop up, right? It's going to pop upward like that. If you bend it that way, it's going to pop up. And that creates this shape, that shape, which if you put some eyeballs on this, that's a sad face. You get sad faces when you have negative emotions. So because this external moment, remember that this is the external one, because our external moment is making us sad right now, that means that the internal moment is going to be the opposite. So that means internal is equal to happy face, the opposite. And the opposite is positive emotions, right? You're happy when you're positive. So cool, so cool. You can go away now, bud. Nope. Whatever, he'll be there. So we just determined that this wonderful 10 kip foot applied point moment, whereas externally he is making the sad face, which is very negative, internally he's going to make us happy. So that means we're going to go positive from where we are right now. We're at minus 6.3, and we're going to be happy. So we're going to go up 10. So now we're going to be at a grand total of 3.7. Ta-da. Assuming I can do math correctly. So we're going to go up to 3.7. That's maybe about right there. So ta-da. And now we can continue about our merry way. That was our point moment. Don't forget to do our degree of curvature. That's 1 degree. Shame on me. So now we're going to continue along. So then what's this? This rectangle is what we're going to do next. It's negative. So again, we're at 3.7 and we're subtracting whatever the area of that rectangle is. So base of 2 feet, height of 2.1. So we're going to get that to be minus 0.5. Awkward. Yep, he's a little small there. So we're at minus 0.5. Again, that was a 0 degree, so this is going to become a 1 degree. A little joyous thing he is there. That's really hard to shade in, but is what it is. 1 degree. Ta-da! Okay, cool. Next up, swap to a new fun color here. Next up, we've got, ooh, that's not going to look good. We'll do this pinky thing. We got this big ol' rectangle here. So again, where are we at right now? We're at negative 0.5. We're going to go down a bit more. Yep, and the area of that rectangle is, of course, 3 feet times his total height of 9.1. And that's going to give us negative 27.8. So woohoo, he's going to shoot down here. We'll just go down there at 27.8. Again, that's a 0 degree, so this is going to be a 1 degree. So believe it or not, that's going to be a straight line. Wee-hee. There we go. So that's 1 degree as well. We can shade that guy in. Then what? Ooh, finally, some positive stuff going on here. Who doesn't like the positive stuff? So again, we're going to go one little rectangle at a time. So we've got this positive one. I'm going to kind of scoot over just a little bit over here so we can remember we're at negative moments in blue. So we're negative 27.8. We're doing positive now. Shear's positive. So positive, what's the area of that rectangle? That's 2 times 7. And we're going to get that to be negative 13.8. Yeah, it wasn't enough. Sorry, so we're going to go up to negative 13.8. That's maybe about there. So 13.8, that was a box. That's a 0 degree slope, so this is going to be a 1 degree. So again, straight line here. Straight line there, so he's 1 degree. Then, oh, this one's going to get spicy. This little homie is fun because he is not just a triangle. Let me blow up this picture for you real quick over here. He looks like this. He's at 1. I don't think we labeled that. Shame on us. He's at 1 and 7. 1 and 7. But this is the shear diagram. So yes, he is a 1 degree curve. He is a 1 degree curve. But you need to take the area of this whole glorious thing. So I'm going to do it by breaking it into 2 separate things. I'm going to say that's area 1 and that's area 2. Because you know why? Because I don't remember what the hell the equation of a trapezoid is for area. But I do know that it's a rectangle and a triangle, and I got that. So we are at, that distance is 2 feet, by the way. So we're at minus 13.8. This is all positive, so I'm going to start area 1. I'm going to add, we're doing area 1 here. It's 1/2 the base of 2 feet. The total height, this is 1, so the total height of this triangle is 7 minus 1, which is 6. Okay, so that's the area of, I'm going to circle that. This is area 1. But wait, there's more. Now I'm going to add in area 2. Area 2 is just a rectangle, so he's base 2 feet, height of 1 kip per foot. So again, this is area 2. So what I'm going to end up with, gosh, keep scooting this screen. We're going to end up with minus 5.8. So all of that, we're going to get up here to minus 5.8, maybe about right there. But this is a 2 degree, right? Because this is 1 degree over here for the shear. We got a 2 degree for a moment. So real quick, let's briefly do our 2-point rule. So I'm looking at this shape and I'm saying this is positive, right? Shear is positive, therefore moment goes up. So I have point 1, this is my first point, and then I've got point 2 because moment's going up. This is my second point. So the shape of my graph is going to be something like this, where I go from the first point to the second point. Okay, the actual points are based on, of course, this is the first point here, and this is the second point. The actual points are based on these values, but I'm just talking shape right here. So when I'm looking at this dude, I'm looking at this line right here. On which side is it bigger, and on which side is it smaller? This side is a hell of a lot bigger than that side. I think we'd all agree. So therefore, the slope on the bigger side is going to be big slope. Big slope, if you think of the equation of a line, big slope, very, 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 very big slope is a vertical line. And a very, very, very small slope on the second point is a horizontal line. And now, doing that, I'm going to connect, following this slope out, I'm going to try and connect these two together, and that is the shape. So it is going to be a going down kind of circle, and that is a 2nd degree. So that's what I'm going to draw over here, connecting my two things. So it's going to be like this. That was ugly. This is why we label everything, because these are absolutely atrocious. We'll try that again. Oh, looks slightly better. So again, that's a 2 degree. And this we said was at 5.8. Okay, that was just atrocious as well. 5.8. All right, lastly, we do have one more little triangle. That's this guy. He is just a triangle, no funny business. So he is just a triangle. So let us figure out him. So again, we're at negative 5.8. That's where we're starting. This is positive, so we're going to go up. And again, the area of a triangle is 1/2. The base is 2 feet. The height of that is 6. So 5.8 negative plus 6, you're seeing it's 0.2. And you're like, uh-oh, that's not 0. And the reason it's not 0 is because of all of these. You see all of these, all of these, all of these decimal points. Every time we had one of these decimal points, which probably came from these decimal points in here, wasn't that lovely, which, let me remind you, came from these decimal points right here. Because we rounded at legitimately any point in time, which, yeah, is going to be that point in time, because we rounded, we now have ourselves not ending at 0. But 0.2 is pretty much 0, so we're good. We're just gonna fake it over here and we're coming back to 0. But again, that was a 1 degree slope, so we're at 2 degree, and as you follow literally what I just said just a few seconds ago, because it is the same shape. Yep, we got the bigger one first, so he's starting out pretty vertical, he's ending pretty flat. That's 2 degree slope, bam, there we go. So we have this very glorious looking thing. And the only other thing I want to talk to you about is finding distances for right here. Technically at this point, we're not going from moment into what would be next, actually the slope of the beam. We're not going to do that, and then from slope we go to deflection. But we're not going to do that graphically, because that doesn't really make too much sense. So this isn't very important to find this distance, but it is really good to label our distances. So again, that's 2 feet, that's 2 feet, that's 2 feet, that was 3 feet. That goofy crap we're going to come to here in a second, that's 3 feet. So how do I find that? And the reason I'm going to cover this is because you'll probably run into it a lot more in terms of shear going into moment. So how we do it is with similar triangles. And no, we're not relating the big triangle to the small triangle. What we really have is, I'm going to blow this up here for just a second. We have it looking like this. Okay, but this is 0.5, this is on the negative side, and this is the positive side, and this is up here at a 3.7. Okay, that's what we have actually going on if we just kind of blew it up. And note, we're not relating big triangle to midget triangle. That's not what we're relating. Those are wrong. What we are going to relate, though, is the big triangle, but to something else, because we don't know x on either of these, right? We want to find what x is, and obviously this other distance over here is whatever 2 feet minus x is. So you can't relate the two small triangles that we have drawn because they both have x and you don't know x. So that gets you nowhere. So we need one that we do know. And what we do know is we're going to fake it. What we do know is this. Right? What we do know is this triangle. Right? The full distance from here to here is 2. Because the small one is x, the other one's 2 feet minus x. So we know that that full distance is 2. The full height of the triangle is whatever 3.7 plus 0.5 is, right? Because we went down 0.5 here, and this is up 3.7. So the grand total is, I have to do that math in my head, 4.2. So what we're relating here is the big triangle, whose base is 2 feet, whose height is 4.2 feet, assuming I can do math, or 4.2 kips there, to the other triangle, which is x we want to know, and a height of 3.7. So if I really want to find what x is, I can relate sames to sames or lefts to rights. Either way doesn't matter. I'll do lefts and rights, but I'm going to do right first. I'm going to put x on top because that always makes things easier. So x is to 3.7, so things on my right is equal to, same bottom first, 2 feet is to 4.2 kips. So really, if I wanted to find x, x would be 2 over 4.2 times 3.7. Whatever that is x. And you could then go plug that back in up here. That's x. Bam. But because we're not going to go and do the slope diagram after this, it is kind of irrelevant that you actually label that. But good on you. Good on you for labeling it. And there, in a hot mess, is our shear and moment diagram for that beautiful, beautiful beam that we did as an example.